I got a request from one of my subscribers if I would do some motion graphs videos. So here it is. I'm looking at the most typical ones that have come up at A level over the last few years. And so here's a classic example, skydiver jumping from plane. It says the graph shows the velocity over time. So we have velocity time graph from the instant she left the plane to just before the parachute opened. Fair enough. We want to determine the acceleration of the skydiver. Now, we know that the gradient of a velocity time graph gives us acceleration. The problem that we may have is, of course, if the acceleration time graph is curved, how do you find the gradient? This comes up an awful lot. For this, you have to draw a tangent to the curve, and you have to be very skilled at this. So let's have a go. We want it at 4 seconds. I'm going to get my little ruler out. I'm going to zoom into 4 seconds and have a look. So 4 seconds is right there. When you draw a tangent, you've got to make sure that you are just touching the line at the 4 second point. And check, and this is why you have a see-through ruler, preferably 30 centimeters long. Check that either side of your ruler, this is not so easy on a computer, but either side of your ruler, the line slopes away from that point. And so you're then just going to draw in your line as your tangent to the curve. Now, you can see that my tangent is not actually touching there, again because of the settings when you use a computer ruler like this. But that is the idea, and it is essential to have a see-through ruler to do this properly. So the first mark here will be for an attempt to draw a tangent to that curve. Any attempt. So even if your tangent isn't great, the fact that you know you're supposed to draw a tangent will get you that mark. The second mark here is for showing the examiner that you've attempted to calculate the gradient. So the change in y, and you use as long a line as you can, go all the way through the graph, find out what your change in y is, find out what your change in x is, and then do the change in y over the change in x. So again, even if your tangent isn't great, if you demonstrate that this is what you're doing, then you will get that second mark. The third mark is usually for the answer. So this is where the quality of your tangent comes in. And at this point, you should be getting an answer between 1.4 and 1.6 meters per second squared. So if your tangent is off, you won't lie between those points. And you see there is quite a generous range here. But I say it's quite a generous range. It's quite a generous range for a good tangent. Second part of the question says, determine an approximate value for the displacement of the skydiver. Now, there's a reason that they say approximate in a question like this. We should know that the displacement on a velocity time graph is the area under the curve. And because this is a curve and not a straight line across the whole line, then you need to start counting squares. So if we go back up to our graph, they want for the first 16 seconds, that is the entirety of this graph, you need to start counting squares. The first thing to do, of course, is to figure out how much displacement one single large square is. And of course, we've got 5 meters per second times 2 seconds. So that means that each large square is 10 meters. So here you have to demonstrate to the examiner that you are counting these squares somehow. You can put little dots in them. You can write down that the displacement is equal to the area under the graph. Write down that you found out that each square is 10 meters, and then you're just doing the count. And you should find that you have about, remember it said approximately, about 42 squares. Which means we have a displacement of approximately 420 meters. These are the two things you need to be able to do with motion graphs. Find the gradient, whether or not it's a straight line, and find the area and know what each of those represents in terms of the quantity you're trying to find. Another favorite is the bouncing ball. So balls drop from rest at a height above the ground, the ball bounced back up to half its initial height, which graph shows the velocity. Now, of course, people are tempted to go with B because they're thinking displacement time graph and not velocity, and they see half the height and they think, well, it must be B. Of course, remember this is a velocity time graph. So if you have a ball and you drop the ball, it hits the ground and it bounces back up. What's going to happen to the ball is it's going to start from a zero velocity and increase its velocity to a maximum just before it hits the ground. So we're looking for a graph where the velocity is increasing. All of them are. from 0. We then need to have a graph that reverses the direction of the velocity in a very short period of time, because that's what's going to happen. If this is plus v, then we've got minus v in the opposite direction. And it's going to have a maximum minus v there, and then as it rises up, it's going to slow down. And it says the ball bounced back up to half its initial height. We're going to assume that that's where it then stopped bouncing. So we should end up with a velocity of 0 up here again. If we look at our options, the reversing of the direction means that C and D are not possible because there's no reversal of direction. Reversal of direction here means it's got to cross the x-axis. We've already said that bouncing up to half the height doesn't mean half the velocity here. This one reduces its velocity too much, so we're going to go for A. Now, obviously, you have to do that much more quickly in an exam, but when you're practicing it, you get used to the thought process, and then you become faster. Another multiple choice, the graph shows how the velocity varies with time for an object. How does the displacement vary with time for this object? Let's think about what velocity actually means. Velocity is an increase of displacement with time. But you can see that when the velocity is increasing, we're going to cover an increasing amount of distance or displacement over time. So we should see that we're getting a curve, an increasing amount of displacement, and then once the velocity goes constant here, we'll have a fixed amount of displacement being covered over that time. So this means that A is not possible. For a start, for the second part of the graph, they're saying there's no displacement over time. And that's not true. We still have a velocity. The velocity has not dropped to 0. In the second one, we have the same problem. It's a misinterpretation that people might have where they think the velocity has dropped to 0 because it's become constant, but that's not true. Part C has got the first part of it correct in that we're getting a curve, so the amount of displacement that we cover is increasing over time because our velocity is increasing. But the problem is with the second part, and there, again, we've hit a constant displacement, which means our displacement is not increasing even though we're still moving with a constant velocity. By a process of elimination, it's D, but if we look at D, we can see we've got the right curve at the start. So as our velocity increases, we're covering more and more distance. And then we end up with a straight line for our displacement because our velocity has become constant. And so every second we're covering the same amount of distance. The last one I'm going to do today, very similar to the first one, but a slightly different sort of question. It's part 4. The first few parts was about a machine. The tool on the machine should not travel with a speed any larger than 0.8 meters per second. The graph shows how the displacement varies with time for the downward stroke of the moving tool. The question is, deduce whether this speed is exceeded by the moving tool. It's the same sort of question, just slightly disguised, and you can see there's quite a large number of marks available for this. So again, we've got a displacement time graph. Is the speed going to be exceeded by the moving tool? Well, we should know that speed or velocity, in this case, because we're moving in a single direction, we can use those terms interchangeably, is the gradient of a displacement time graph. And so we need to see where the maximum gradient of this graph is. Put a tangent to the curve at that point, and then see if we get a speed greater than 0.8 meters per second from that steepest possible tangent. Our first mark is going to be for drawing a tangent. I'll have a go, but again with the computer it's not as easy as if you're doing this, but I'll have a go because it'll demonstrate to you how you find the steepest. Now clearly we've got 0 degrees there. Your ruler won't show 0 degrees, so you're just looking at the steepest part of the line. So you want to go along here and find the point of the line where you are going to get the steepest possible gradient. It's going to be somewhere along there. And again, you put in a line that covers the whole side of that graph because you want to use the largest gradient triangle possible. So you put your tangent line in, and then you go ahead and calculate the gradient of that. The second mark here is for the large triangle. And the third mark is for the gradient calculation attempt. Now again, it doesn't matter the quality of your tangent at this point, because they just want to see you at least try to do it correctly. It's only in the fourth mark that the quality of your tangent becomes important. And you should get somewhere in the range of 0.60 to 0.80 meters per second. They're expecting an answer of 0.68, but that is the range that they give you. So again, that is the range that you'll be allowed your tangent to sit within. And of course, you need to have a conclusion at the end of this and to say that therefore the speed is not exceeded. Remember, anytime you see deduce, you have to draw a conclusion at the bottom of your question or you will not get that fourth mark. So if you can, follow these rules. If it's a curve, you draw a tangent, a large triangle, attempt to calculate a gradient, you are going to pick up at least most of the marks for a motion graph question. And these are the trickiest ones, the ones with the curves.